A satellite of mass 200 kilograms is released from rest a distance of h 1.5 times 10 to the 6 meters above the surface of the moon. With what speed is it traveling when it hits the surface? Mass of the moon is that, so it's about 100th of Earth, and our moon is 1.738 times 10 to the 6, about a third of the radius. Okay, and so your first thought here is draw a picture, because pictures are nice. Ooh, I could use a circle. Circle. Very nice. So we have a circle. Boom, this will be our moon. Yep. And then we have, we'll say blue for our satellite. Be something kind of like this. Hop, 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 a little bit teeny legs. And then draw it falling to the ground. So your first thought is, okay, so why is it that satellites don't normally just fall to the ground randomly? And the idea here is satellites normally have a tangential velocity, and that gives us a centripetal acceleration outward. So centripetal acceleration is v squared over r, but we're told that this is released from rest, so the acceleration outward is going to be 0 squared over r. Yep. And therefore, it's just going to fall, just due to gravity. So this will be force gravity. Oops, so I can get rid of some of these guys. Don't want to get rid of that. And so we want to find out how fast it's traveling when it hits the surface of the moon. And the way we're going to do that is just an energy balance. So your thought process should be, all right, energy potential initial plus energy kinetic initial equals energy potential final. Whoop. Plus energy kinetic final. So we have, let's see here, it's going to have some initial potential energy due to its height, but it's going to start from rest, so this will be 0. We're going to say the surface isn't 0, and then it's going to have some kinetic energy. So I'm going to rearrange this as change in energy potential, so moving this one over there, will equal energy kinetic final. Now I'm trying to think of this from an intuitive point of view. So we have some work done, which is how we get this energy, by a force, this is gravity, and that gives us a final kinetic energy. So the way you convert a force to work, to energy, work and energy are pretty much interchangeable, is through the formula work equals integral F dot dr. And these are both vectors, and that's dot product. So we're going to have our force here is going to be gravity. And our kinetic energy here is going to be 1/2 mv squared. So what we want to do is we want to find out how much energy is created, so to speak, from this force of gravity from the satellite moving towards the moon. So we're going to set up their equation like this, and that's going to give us our change in potential energy. So one other thought you might be having at this point is like, all right, we already know the equation for energy potential. It's mass times gravity times height. Well, that's not entirely true. This right here is an approximation. And I'll probably show it to you later as we go through this problem where that approximation comes from. So, but you can't use that for here, and you'll see why later. So start here, we're going to have this equation. So we're going to have integral F dot dr, arrow, arrow, vectors, equals 1/2 mv squared. This is the equation we're going to solve for. So our force, in this case, is force of gravity. So force gravity is going to be, I just used purple, just use darker blue. So force gravity, Fg equals big G mass 1, mass 2, all over r squared. So we're going to plug that into the equation. One thing to note here is this dot product, these are vectors, but the force and the direction of motion are the same. So dot product, you normally think of cosine of theta. In this case, theta will be 0. So cosine of 0 will be 1, specifically positive 1. So we can basically just do force times dr. So we get integral G mass 1, mass 2, and I'm going to write this instead as times r to the negative second. It's the same thing. It's just more obviously the power rule when we take the integral. dr. Gravity, mass 1 and mass 2. This will be the satellite. That'll be the moon. Or we'll reverse it. We'll say it that way. That's good. Satellite, moon. Those will be constants. So we can pull them out. So g, mass 1, mass 2, integral, r to the negative 2 dr. Like so. Now we do the power rule on r to the negative 7, g m1, m2. And this will be from R initial to R final. So before the satellites fall in to after the satellites fall in. Then we will have, so this will be R to the negative 1 times negative 1. But we can take that negative 1 and just switch the limits of integration. So normally it would be R final on top, R initial on bottom. And so now we're left with an equation of Gm1 mass 1 mass 2 of 1 over R1, 1 over R initial minus 1 over R final. And this will equal 1/2 mv squared. Now this makes it, at this point we can solve it pretty readily. So we're going to rewrite though this R initial as, now we'll probably look at it as, let's see here. We have the radius of the moon and we have the height above the surface. So R initial will equal R moon plus h. So okay. So we'll rewrite this one real quick. Gravity constant, mass 1, mass 2, 1 over, I'm going to just leave this as big R plus h minus 1 over R. So this is the energy, potential energy due to the satellite falling. So at this point now, we're going to look and see how this compares to our MGH equation. So if we say that, in this case, R equals radius of the Earth, and h is just the height above the Earth that we're falling from. And if we look at this equation, we can kind of simplify things. So we do G m1, m2, and this simplifies, so we kind of combine these. So this would be r minus r plus h. Yep. All over r plus h times r. So then we simplify this one more time. So these r's are going to cancel. We're going to have g mass 1 mass 2 times h over, and then we simplify this part, it'll be r squared plus rh. H, now we're going to say that h, I guess I can make this a big H. We're going to say that h is very small with respect to r. So the idea here is this is r, this is h, and so we have a very small, h is small. This is kind of like a limit. Limit as h approaches 0. So this part is going to go away, go to 0, because r times something small is going to be 0, more or less. And this is going to be a constant. And so what we're left with is gravity mass 1. We'll call this, whatever. This one will be just the mass of the object. This will be mass Earth over r squared times h. And so if we, everything here, I'll move this mass 1 over here. This part right here will be the same, because when we're talking about dropping things, we think of the equation energy potential equals mass times gravity times height. So this is the mass, this is the height, and this right here is going to be g. What we're used to is our gravity constant. So plugging numbers into this, we have g, which is 6.67 times 10 to the negative 11th. We have the mass of the Earth, which is 6 times 10 to the 24th kilograms. And then the radius, which is 6.4 times 10 to the 6 meters squared. And then simplifying all of this a little bit, we have 6.67, we have a 6, we have 24 minus 11 is 10 to the 13th, we have 6.4 squared times 10 to the 6 times 2 is 12, that gives us 10 there. And then we have, pull up the calculator, on clear, 6.67 times 6 divided by 6.4 squared, multiplied by 10, and we get about 9.77. If we use more accurate numbers, we'd get a more accurate result, but that says this is where the g, or gravity, is 9.8 meters per second squared. That's where this comes from. So it all came from, backtracking a little bit, this integral that we solved over here. So that was a sidebar tangent. Whoop. Now that we've done that, kind of delete that. Whew, this is getting far more involved than I expected. Okay, so we have this equation right here. And we're going to solve this. Yep, we're going to say that this equals 1/2 m1 v squared. The mass 1 will cancel. That's the mass of the satellite. And so now we're just going to solve for v squared. So moving this equation over here, g is 6.67 times 10 to the negative 11th. That's just the gravitational constant. Mass 2, which is the mass of the moon, I think they gave it to us here, is 7.4 times 10 to the 22nd. So we have 7.4 times 10 to the 22nd. And then we'll multiply this by 1 over, and then we have r plus h. R is 1.738 times 10 to the 6th. 1.738 times 10 to the 6th. 1.738 times 10 to the 6th. And we'll add on to that the height of the satellite, which is h. 1.5 times 10 to the 6th. Plus 1.5 times 10 to the 6th. Minus, and we'll do 1.738 times 10 to the 6th. Okay, so now we're going to solve this. Then this will be equal to 1/2 v squared. So looking at this, that goes to 10 to the 11th. Ooh, let's grab a calculator. So we'll do 6.67 times 7.4. So we have 49.358. We'll take out the 10 to the 6th here and put that up top. So this will be 10 to the negative 6 times 10 to the 11th, which gives us times 10 to the 5th, times quantity. This is 1 divided by quantity, 1.738 plus 1.5. And then we'll subtract from that 1 over 1.738. This should give us a number, 0.266. Probably messed up somewhere on a sign. We'll address that later. So we have 49.358. 49.358 times, I'll say negative 49.358 just to get rid of my negative sign. And we're left with, times 10 to the 5th. There we go. That gives us a relatively big number. 131.5594. 5594. And this is equal to 1/2 v squared, where v squared is the speed of the satellite. I know this is dragging on way too long, times 2, second square root, second answer. And this should give us our velocity. And velocity equals 1622 meters per second. So 1622 meters per second. Interesting. So 1622 meters per second. Let's see if that's a possible answer. I know, so much work. Did not mean for it to drag on that far. You can now see why people simplify potential energy to mass times gravity times height. So our final velocity is going to be 1622 meters per second. We had a satellite up here. It was falling to the planet, the satellite, the moon. And as it was falling, it was picking up speed, converting potential energy to kinetic energy. And the way we account for that is through the equation work equals integral F dot dr. We know that force is, for gravity, is g times mass 1 times mass 2 over r squared. We then plug that in. We take the integral, do some craziness. It feels like craziness, but this is a integration you should be able to do. It's a power rule. We then get an answer for the potential energy in terms of 1 over r plus h minus 1 over r. We set that equal to 1/2 mv squared, do some algebra, solve the problem, and we got our final answer of 1622 meters per second. So reasonable amount of work to find the answer, but not too hard, and no individual step is all that complicated. Hope this helped. Hope this kind of crystallized the concept for you and helped you understand kind of where it goes. So that's what I have for this problem. I will see you next time.